Hello and welcome to this lecture. We saw the definition of the derivative and what it means in terms of a graphical interpretation, this tangential line and its slope, etc. And we saw how to figure out whether derivatives exist just graphically looking at it and doing some operations with it, right? So now we will start looking at how to compute the derivative of a function. A function is given as an expression involving x, right? How do you compute the derivative? There are some standard differentiation rules. We will just quickly go through them and try to use them. And you'll see this will be very similar to how we computed limits of sequences and how we computed limits for functions, right? It's the same process. We will go from simple cases to more complicated cases using some rules or logic or something like that. Okay, so that's what we'll do. So the first easy cases we've always considered are constant and identity functions. So supposing f of x is a constant, it's just a flat line, right? Constant throughout for all x. Then how do you compute its derivative? It turns out derivative is very easy for it. Let's look at the definition, right? F of x naught plus h minus f of x naught divided by h. What is f of x naught plus h? F of x naught plus h is just c. What is f of x naught? That is also c. So c minus c divided by h, and that goes to 0. And now you can take limits on both sides and you will get f prime of x naught is this limit, which is simply 0. Okay, so you see for the constant function, for the constant function the derivative is 0. Very quick and easy derivation. Now you can say do the same thing for the identity function, and I have just gone through this very quickly here. Again, f of x naught plus h is c plus h, f of x naught is c, right? F of x is x, right? This is the identity function. C plus h minus c divided by h, and that's going to be 1. Okay, so now you can take limits on both sides and you'll get f prime of x naught is 1. Okay, so point is now you can see that both these functions, the constant function and the identity function, are differentiable at all points on the real line, right? So that's all x naught. You remember how we write down x naught, right? What is this x naught? For any x naught, f prime of x naught exists for both these functions. That's what I mean by saying differentiable at all points on the real line, and the derivatives are 0 and 1. For the constant it's 0, for x it's 1. Okay, very easy derivation. Okay, now these are the known cases, and just like before, we will go from these known easy cases to more and more complicated functions in a very simple way using logic. Okay, so as long as you remember the logic, you'll see that it's very easy to remember derivatives and how they work. Okay, so this is where the differentiation rules come in. We know the two things. Notice how I have written it here. This is a very sort of interesting simple notation that succinctly says what it is. C is my constant function. I put this sort of brackets around it, and then I put a prime here. Okay, so c prime, which is the derivative of c, that is 0. Likewise here x, and then I put a bracket around it and put a prime here to indicate that I'm taking a derivative here, x prime equals 1. Very nice, isn't it? It's a succinct, clean notation to denote derivative. Okay, so now let's say we have two functions f and g for which the derivatives exist at x naught and they are finite. Okay, so these are simple assumptions that we start with. So these could be some known functions, and how do we do operations on f and g, and how does the derivative behave with respect to that? That's differentiation. No? For limits also we did the same thing. We'll do the same thing for differentiation. The first operation is scaling, addition and subtraction. Here the derivative behaves in a very linear fashion. So this is called a linear type of behavior. What is linear? If I scale the function and then take its derivative, it's the same as taking the derivative first and then scaling it. Okay, so this is like this, any constant c will come out of the derivative and you can do c times f prime of x naught. Okay, so it's very useful. So scaling is very useful. We'll see how to put it to use soon enough. The next is the addition of these two. Supposing I do f of x naught plus g of x naught and then look at its derivative. So notice what I'm doing here. This is sort of like sort of bizarre sort of notation, and I'll quickly correct it. This is not very nice in the sense that, see, I know what f prime of x naught is. I hope you understand what I mean by saying f of x naught plus g of x naught prime. Okay, so this is not very good notation. It's I should say the function f plus g prime x naught, right? So that's the correct way of denoting it. Maybe I should show that here. Okay, the correct notation will be something like this: f plus g is my function, and then prime evaluated at x naught. Okay, so this is probably a better notation, but is a bit confusing and people don't really understand it. So I'm using this very sort of ambiguous looking notation, this c f of x naught prime. I hope you stay with me, understand what I mean by this. So basically I'm looking at the function f plus g and its derivative at x naught. Good enough, I think. Okay, so this, it turns out, the addition also, differentiation distributes over addition very linearly. So you can simply take the derivative of f at x naught and add it to the derivative of g at x naught, and you will get the entire derivative. So these things can be proved. It's very easy to prove these things. I'm going to show you a slightly more difficult proof, and then from there you can work out these proofs. So I'll leave these proofs as exercises for you. You can look at these things and post the proofs on the discourse forum and discuss about it, and then it'll be very interesting for you to discuss that in the forum. Okay, so I'm not going to go through all these proofs in the class, but I will show you a couple of interesting differentiation rules proof. Okay, the same thing holds for minus. So f of x naught minus g of x naught prime is just f prime minus g prime. Okay, so now we go to more complicated operations, multiplication, composition and division. So here the derivative does very different looking things. Okay, so we remember when we did limits, multiplication, composition, composition we didn't quite do, multiplication and division had a very simple rule with respect to limit. The limit simply went inside, okay, whether it's multiplication or division. But this derivative will do something slightly different here. Okay, so notice what is going on here. If I multiply fg and then look at its derivative at x naught, okay, that guy is actually f of x naught times the derivative of g naught plus f prime of x naught times the derivative of g naught. Okay, so this is slightly different. F of x naught times the derivative of g at x naught plus f prime of x naught times the g of x naught. So you see it's sort of interesting how this comes. I'm going to show you a proof of this soon enough to see how to argue why this is true. So you see it's not very simple. So it's not like product of two things derivative is simply derivative of f times derivative of g. No, it's not true. Okay, so it is f times g prime plus f prime times g. This is a little bit more involved here. So I'll show you a proof and then sort of show you examples of how to use it, and this is how you do for product. Okay, now composition is a very interesting and important operation. What is this f of g of x naught? Okay, so let me just give you a few examples to illustrate what I mean by this. Okay, so you may have a very easy function, like for instance f of x is x, and or maybe let me just take a very slightly more different function. F of x is 1 minus x squared, right? So this is a quadratic function, you know what this is. And then I may have a function which is the square root of 1 minus x. Okay, so let's just do this. So two different functions here. What is the meaning of f of g of x? What is this composition? So you take g of x and substitute it as x in this formula. Okay, so what does that mean? I take it as f of square root of 1 minus x. Wherever I have x, I am going to put square root of 1 minus x. 1 minus square root of 1 minus x whole square. Do you get that? Okay, so you look at this composition. So this is the way compositions work. F of g of x, and then you will get 1 minus, I get this is 1 minus x, and it ends up being x. Look at that magic, right? So you have 1 minus x squared, and a g of x is square root of 1 minus x, and f of g of x ended up being x. What do you think will happen to g of f of x? I can do this also, no? I can do this composition also. Take this guy and substitute wherever you have x in g, right? So g of 1 minus x squared, and that is square root of 1 minus x squared, and that's also x. Very interesting, isn't it? So do you see why that's x? Okay, so you see that. So these compositions have this very interesting thing. So you can also do various types of compositions. You can take f of x to be square root of x, and then g of x to be, I don't know, I'm doing this 1 plus x. Okay, so if I do this, what will be f of g of x? It will be f of, so as you get more and more experienced with this, you don't need to write all these things in gory detail. When you say f of g of x, I am going to put square root and put 1 plus x there. That's it. I get it very immediately, right? G of f of x, if I want to do, it's going to be again 1 plus, instead of x, I'm going to put root x. That's all. Okay. So what compositions allow you to do? Compositions occur all the time. Okay. Anytime you see a function, you have to immediately visualize it as a composition of multiple simpler functions. Okay. So this is sort of like divide and conquer. You take some simple functions which you know well, and then you compose them and you get very complex sort of functions. Okay. You know root x maybe quite well, you know 1 quite well. Now this is 1 plus root x, which you can think of as addition of 1 and root x, right? So you take the root x, then shift it up by 1. Like, notice how the composition sort of helps you in picturing the function, understanding the function and all that. Okay. So in general, the composed function is going to be slightly more complicated than each of the individual functions, or maybe not necessarily, right? Notice these two functions here, they worked out very easily for you, right? F of g of x, it just ended up being x. Sometimes the composition is easy as well, right? So it's all interesting things happen with composition. Hopefully this composition is clear to you. So now what I'm asking here is, supposing I do such a composition, f of g of x, x naught, let's say, f of g of x, its derivative f of g, that's derivative at x naught, okay, what will that be in terms of the derivatives of f and g? It turns out there is a formula there and there's some condition. Notice what is going on here. It's basically f prime evaluated at g of x naught. Okay, so you have the derivative f prime evaluated at g of x naught. So this guy has to exist, right? I have not added that here. I put only f prime of x naught existing. But for this composition rule to be true, this rule is also called the chain rule or the composition rule. For this chain rule to be true, this f prime has to exist not only at, has to exist at g of x naught. Okay, maybe it doesn't even need to exist at x naught, right? It needs to exist at g of x naught. So this one has a slightly different condition. I have not put it out here, but this is needed. Okay, so then you have f prime of g of x naught times g prime of x naught. Okay, so notice how this is not a, I showed you very similar examples. It's not like a symmetric operation between f and g, right? F of g is different from g of f. Okay, so if you do g of f, then the formula changes. This becomes g, this becomes f, right? So you see that the derivative also changes. But this formula is very, very powerful. We will use it soon enough in many of our ideas and derivations. So you see this f prime evaluated at g of x naught times g prime of x naught. Okay, and then you have, so we'll use all these things in the example section. You'll see when it comes there, I will show you detailed illustrations of how I'm using all these things. I'm not going to illustrate them right away, but I'll just walk you through the formula and then you'll do. Okay, the last formula we're going to talk about, the differentiation rule we're going to talk about, is the division rule. Supposing you do f of x naught divided by g of x naught. Clearly here g of x naught should not be 0. If g of x naught is 0, this division is not valid. So that condition is an additional condition. I have not stated here. You need this for this rule. This is a complicated looking formula here, right? So many of us probably have seen this before and we mugged it up. It can be proved. I will show you the proof for the product rule and the composition rule. Some reasonably good proofs will show you. Maybe not all the gory details, but some proof we'll see. But proof for the division rule is not that difficult. You can try it, give it a shot, and once again, if you find a proof or if you can do the proof yourself, you can post it on the forum and be happy about it, right? So let everybody know. So the formula here is a little bit more complicated. In the denominator, you have g of x naught squared, and in the numerator, you have g of x naught times f prime of x naught minus g prime of x naught times f of x naught. It's a handful. It's a reasonably big formula to remember, and if you use it enough, you will remember it very well. Okay, so these are all the differentiation rules. So you have these couple of very simple known cases. And can we use all these rules to our to good effect and compute derivatives for more and more functions, right? So that's the interesting challenge here. But before I close, basically what these rules tell you is, if f and g are differentiable at x naught, then a whole slew of other functions are also differentiable at x naught. See, scaled version of f of x plus or minus g of x, product of f of x and g of x, the quotient f of x by g of x, if g of x naught is not 0, and then the composition f of g of x. Of course, this requires f prime to be differentiable at g of x naught. Okay, so all of these things are also differentiable at x naught. Okay, so these are differentiation rules. Let me just quickly show you the proof of these two. We'll just walk through that and then move on and see how to use it to derive derivatives for more and more functions. Okay, so first quick proof. Before that, I want to say a word about how we simplify notation even further. Okay, this leads to all sorts of abuse of notation and confusion, but this is so common that people have used this differentiation so many times. Once you get totally used to it, you don't want to keep carrying on this x naught, x naught, x naught. People will simply say f prime of x, g prime of x. In their mind, x is some variable, right? Of course, it's like a free variable, but they'll think of x as taking a particular value, like an x naught, right? And instead of saying x naught, x naught, x naught, simply say x. And in your mind, you differentiate the dummy variable being used for defining the function, as well as the place where you're differentiating as the same. Okay, so it's not too big a notational confusion in your head. So we can just use it like that. Okay, so notice I've just dropped the x naught here, simply saying x, 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 x. So in your mind, this is like much simpler notation. It looks cleaner, and as we go forward, we'll be using that as well. So notice I've done that here also, right? X prime equals 1. For every x, this is true. So I've done that here also. It's a very clean sort of notation, and this works out okay. All right, and let's see the proof for the product rule and the composition rule, and then more. Okay, proof of the product rule. So first start with the definition, right? So f times g at x I want to take derivative of. What is the definition? It's the limit as h tending to 0 of f times g evaluated at x plus h minus f times g evaluated at x, right? X plus h, x plus h, x, x divided by h. This is the formula, right? So now I have to convert somehow all these guys into something involving f prime g prime. So I have to somehow factor this guy, right? This one is not factoring in any way. For this, there is a trick. Okay, so this is a little trick. Once again, like I said, all of these math ideas use some nice little trick here, something that won't change anything. Remember good old parallelogram area that we computed, you just move something so that nothing changes. So here also we do something, we'll do something so that nothing changes. Here is what it is. Okay, so you take this guy f of x plus h, g of x plus h minus f of x, g of x, and notice what I've done here. I've subtracted something minus f of x, g of x, and then added it back again. Okay, nothing has changed, right? I've just subtracted f of x, g of x plus h, then added it back again. But here immediately you see I have this wonderful little f of x plus h minus f of x times g of x plus h plus f of x times g of x plus h minus g of x. Now this is starting to look like a derivative for f and derivative for g. This little trick that I played with this, not changing anything, is giving me a different form for this expression, f of x plus h, g of x plus h minus f of x, g of x. And I'm beginning to see these sort of possibilities here. So I can do divide by h on both sides. Notice that I get this division by h here and this division by h here. Now we can take limits on both sides. If you take limits on both sides, you get the derivative of product on the left hand side, and what you get here magically is f prime of x. This limit as h tends to 0 is f prime of x. This limit as h tends to 0 is just g of x. This is just f of x. This limit as h tends to 0 is g prime of x. Notice how very easily we could derive the product rule. So the product rule has a very simple derivation. Hope you like that. Okay. Now the chain rule is not so simple. We won't give a complete rigorous proof, but I'll point you to the main argument. Okay. Once again, here's the composition and the definition. Okay, always start with the definition. The definition is easy to write down. Limit as h tending to 0, f of g of x plus h minus f of g of x divided by h. Okay. Once again, I have to somehow bring in terms that look like the derivative of f prime at g of x and the derivative of g prime. So here again, I will do something that doesn't change anything. Okay, here is a little trick. Once again, a trick which doesn't change anything, right? This is the expression, and I've divided by g of x plus h minus g of x multiplied by g of x plus h minus g of x. So you assume I'll restrict h so that this guys don't become 0. Okay, so you have to do such things. So those are the technical rigorous parts which I am skipping. Okay. So but we can see, as long as these guys are non-zero, this g of x plus h minus g of x, you can divide and multiply, and I have not changed anything. But in the process of not changing anything, now I'm beginning to see derivatives, right? This one looks very much like the derivative of g. If I take limits now, I will get sort of derivative of g. But what about this one, right? So this looks a little bit more complicated. Maybe this is not a derivative, but is this the derivative of f at g of x? That's what I have to see, right? So here we can do what's called a change of variable. Okay. So this is also something that's very common in mathematics. As you go through engineering and science and various applications, you will look at something and you'll do a change of variable. When you do a change of variable, suddenly some expression which looks very difficult to understand or make sense of can become very easy. Okay. So here the change of variable, a very tricky little change of variable. I'm going to say this x tilde, some other variable, is g of x, okay, because I'm looking at the derivative at g of x, right? So let's call it x tilde, and then I'm going to call this h tilde as g of x plus h minus g of x. Okay, so whatever is in the denominator, right? See, I want to make this look like the derivative of f at x tilde, right? So I'm going to put f of x tilde here. I'm going to get h tilde here. Okay, so now when the change of variables happens, you should always be careful about what happens in the limit here. See, I did this change of variables. What happens to the limit as h tends to 0? As h tends to 0, h tilde also tends to 0, right? So that's a nice thing to see. Okay, so that's something you can keep track of. But interestingly, once I make this change of variables, I have this wonderful little expression. Look at what happens to this expression. This expression becomes this expression. And this is something I'm very intimately familiar with, right? F of x tilde plus h tilde minus f of x tilde divided by h tilde. If I push h tilde to 0, this becomes the derivative of f at x tilde, which is exactly what I want. Look at how easily this picture becomes something else. But now I have to tend h to 0. But tending h to 0 and then tending h tilde to 0 are sort of the same thing. Okay, so now that needs a little bit of a technical sort of argument. But we will skip that technical argument, and I'll simply make this as like a reasonable fact that most of you will believe. Limit as h tending to 0 of this guy is also f prime of x tilde. So there is this minor little technical detail. I'm not put a technical thing here, but you can prove this if you like more rigorously. So once you prove this, you're done, right? So the derivative of the composition of f and g is f prime evaluated at g of x times g prime of x. Okay, couple of proofs just to show you that all these things come rigorously from the definition. I'm not just conjuring some trick here or stating some random thing or intuition or anything. From the derivation of the limit definition for the derivative, right? From the definition of the derivative, rigorously, properly, you can simplify and come to these each and every one of these rules. And like I said, for the other rules also, the scaling rule, sum rule, product difference rule, quotient rule, I'll encourage you to find a proof like this yourself. Maybe there'll be some technical points which you can't quite resolve very rigorously, but that's okay. You can learn it later on in life if you're interested. But at least post a proof of this type so that we are happy that everything is correct and proper. So that's the end of this little lecture. We'll move on next to how to use these differentiation rules and start computing derivatives for more and more complicated functions.